Our first presentation this afternoon is from Mr. Chris Crall. Chris is a mechanical engineer with expertise in thermal insulation and energy usage in commercial and industrial facilities. He's currently providing technical consulting services to the National Insulation Association in the areas of building energy standards, energy analysis, heat and moisture transport, and mechanical insulation standards and specifications. Mr. Crall has more than 35 years of experience in research, product development, and technical support on residential, commercial, and industrial insulation applications. Mr. Crall received degrees in mechanical engineering from The Ohio State University and in business from Xavier University, and is a registered professional engineer in my home state of Ohio. Chris, welcome to the podium.
Thank you, Bob, and good afternoon. Let me get started with a little introduction about who I am and who I'm representing. As Bob mentioned, I'm a mechanical engineer. I'm doing some consulting, and right now I'm doing consulting for two organizations, the National Insulation Association and the International Association of Heat and Frost Insulators. Back in 2009, those two organizations got together and created an alliance, and the idea was to begin to think about insulation differently. Insulation in many arenas is the Rodney Dangerfield. We get no respect, and our goal is to change that. So one of the things we got to thinking about was the energy-water nexus, and you've heard a lot about that, and mechanical insulation is an excellent example of the energy-water nexus. And I want to go through some of our codes and standards. Right now, all the current energy codes and standards require some thermal insulation on domestic hot water piping, and the requirements vary. And this is a summary of some of them. I wouldn't say this is all inclusive, but I've listed a few of them. Let me start with the 2012 International Energy Conservation Code. Most of the codes break it down by nominal pipe or tube size, and the IECC requires 1 inch of insulation across the board. The residential code, IECC, states it as an R3, and in most applications, R3 is about a ½ inch of insulation. ASHRAE Standard 90.1 in 2010 modified their requirements, starts out at about 1 inch, kicks up to 1½ inch at about the 1½ inch tube size and pipe size level. You can see California 24, similar. I guess the thing I'm trying to point out is the similarities in the different codes, and even the green codes, the ASHRAE 189 code mirrors the 90.1 code. A little bit of that is timing. As I mentioned, the 2010 was upgraded recently, and the 189 has not caught up. A little bit of an outlier is the 2010 Green Supplement, the IAPMO Green Supplement. It requires a insulation thickness equal to the pipe or tube size up to about 2 inches. It's a little bit different approach. Most of the other approaches are an equal heat loss per area type of thinking. This is an equal heat loss per linear foot of piping type of thinking, which is better. I'm not sure it's 6 of one, half of the other, but I guess the similarity is the thing I want to point out. Look at 1 inch pipe size. Everybody is at 1 inch except the IECC residential. And this is specific to domestic hot water recirculating and heat traced loops. So those are pipe insulation minimum thicknesses. Now let's look at other areas, the non-recirculating piping. These would be the runouts, either runs from the hot water heater to the fixtures, or they would be from the circulating loops to the fixtures. And the requirements vary quite a bit more here. The 2012 IECC requires 1/2 inch for 8 feet, the first 8 feet from the heat source. So if you'll think back to the previous slide, it required 1 inch on the circulating loops, 1/2 inch for the first 8 feet from the heat source. Not sure where that number came from, and I'm not sure what the science behind it. I assume they're talking about limiting the axial heat transfer down the pipe as a leak from the heat source. IECC residential, R3, I'm going to talk about that a little bit more later. The 90.1 per table, per the size table in the previous slide. Again, the 8 foot from the heat source. Title 24, 5 feet from the heat source. ASHRAE 189, 8 feet from the heat source. And again, the IAPMO green supplement requires all the domestic hot water piping to be insulated. So let me talk a little bit more about those two that are circled. First of all, the IECC requirements. And it's somewhat complicated. This is the residential requirement. There's 9 items on that list. And I'm just going to go through them quickly. First of all, the hot water pipe insulation should be a minimum of R3 for the following areas, and that's any piping larger than 3/4 inch nominal diameter. The second item is piping serving more than 1 dwelling unit. Piping from the water heater to kitchen outlets. Piping located outside the conditioned space, all require R3. Piping from the water heater to a distribution manifold. Piping located under a floor slab. Buried piping. Supply and return piping in recirculation systems, R3. And piping with run lengths greater than the maximum run lengths for the nominal pipe diameter given in table 403.4.2, which I've reproduced here. So this table tells you that basically for 3/8 inch piping, anything over 30 feet should be insulated. 3/4 inch piping, anything over 10 feet should be insulated. I guess my thought is, well, what's left? There's not a whole lot left that isn't R3. The green supplement is unique in that it requires insulation on all domestic hot water piping. In addition, the volume of the water in non-recirculating systems is limited to either 32 ounces or 16 ounces. That's 4 cups or 2 cups. 32 ounces is approximately 20 feet of 1/2 inch copper. 16 ounces is approximately 10 feet of 1/2 inch copper. So this approach limits the waste of energy and water in domestic hot water systems. So the question is, why not just insulate all the domestic hot water piping like the green supplement requires? And of course, to answer that question, we have to understand the economics. So I'm going to take you through some of the economics on this. For recirculating loops, it's really a no-brainer. Here's an example calculation. I'm going to assume a 1 inch copper line in still air. I'm going to assume it's insulated with 1 inch of fiberglass insulation. I'm going to assume an operating temperature of 135 degrees Fahrenheit and an ambient of 65 degrees Fahrenheit. And I can calculate the heat loss from the bare pipe as about 39.5 BTU hour per foot per linear feet of that 1 inch piping. And I can also calculate the heat loss from the insulated pipe at about 8.8 BTUs. So the difference, the delta, is about 30.7 BTUs per hour per foot. And that's roughly an 80% reduction bare to insulated piping. If I assume some cost numbers and some operating hours, I can calculate a dollar savings to the tune of about $9.46 per year. I go to RS means and look up 1 inch fiberglass pipe insulation. It gives me $6.12 per foot. So my simple payback period is 0.6 years, less than a year. My return on investment is 155%. So that's a no-brainer. Now, some of the things that went into that calculation are an assumption about the operating hours. That's assuming 8,760 hours per year of operation. May not always be that. May be that in a hospital, may be that in a multifamily residential facility. There's a lot of facilities that may not operate 8,760 hours a year. But if a payback is 0.6 years, even if it's half of that or a quarter of that, it's still a no-brainer. For the cost of energy, I used electric heat, an electric resistance heated hot water heater with a cost of energy of 12 cents a kilowatt hour, which happens to be what I pay in Columbus, Ohio. So again, that's going to vary. You may have a natural gas-fired water heater. You may have a heat pump-fired water heater. Maybe a third of that in energy costs, but still it's a no-brainer. The payback period may not be 0.6 years. It may be 1.2 years. It may be 2.4 years. But circulating loops need to be insulated. No argument there. Really don't need to have that in the code. That's one of those things that's so obvious that that's going to happen anyway, whether it's in the codes or not. Let's take a look at the non-recirculating systems, the branch lines, intermittent use. Here the economics are going to depend on the frequency, duration, and pattern of usage. So let's kind of go through that same calculation, except now we're going to assume a 25-foot run out of 1-inch copper branch line, and we're going to make some assumptions about the usage. We're going to assume 3 showers a day, 20 minutes per day total. That works out to be 122 hours per year of operation. So my dollar savings for 1 foot is 15 cents. My cost to insulate is the same, $6.12 per linear foot. So my simple payback is 41 years. So it's not justified on energy cost savings alone. That's the traditional way that people have thought about insulation. For mechanical insulation, it's based on energy savings only. But we know that there's more to it than that. What about water savings? Let's begin to think about the energy-water nexus. Can insulation reduce the use of water? Reducing water usage reduces the energy required to obtain and treat the water, deliver the water, and to treat and dispose of the water. And we've seen earlier this week that the embedded energy content of potable water varies from 2 to 20 kilowatt hours per 1,000 gallons. And I want to point out that is at the building line. If you heat that hot water to 135 degrees or 140 degrees, you're talking about another 700 kilowatts per 1,000 gallons. So the heating of that water is the big user of energy, and that adds on to the embedded cost of that energy. Let's take a look at a typical hot water usage event. You've probably seen graphs like this in the past, but we really have kind of 3 segments. We have a heat up phase, a use phase, and a cool down phase. And the heat up phase, I've got this drawn pretty much to scale. I've got this at about 30 seconds to maybe a minute that it takes for the water in the fixture to be hot enough to use. I'm showing usable hot water at 105 degrees. That's assuming a storage temperature of 135 and an ambient temperature of 65. So it takes about 30 seconds to a minute to get that hot water to the fixture. Then rapidly comes to kind of a steady state condition. Here I'm showing about a 7-minute shower. At the end of that 7-minute shower, the temperature in the hot water line begins to decay exponentially. I'm showing about a 10-minute decay period on this one out to about 17 minutes. The temperature gets down below the 105-degree hot enough to use threshold temperature. So there's 3 opportunities, 3 phases, the heat up phase, the use phase, and the cool down phase. What about opportunities for savings? What about opportunities during the delivery phase? Will insulating the branch line make that heat up phase shorter? The evidence so far is unclear on that. I've looked back at some of the studies that were done in California where they did an extensive experimental study of heat up times, and if insulation does make a difference, it's very small in that heat up phase. It's found that it takes about 25% more water than the volume of water contained in that piping to get to that heat up phase. And the data I've seen from a study by Mr. Hiller out, I believe was sponsored by the California Energy Commission, shows that that may go from 1.24 to 1.25. So if it does change, it's very little. During the use phase, we've already kind of calculated that in. That's the 122 hours per year of operation, 7 minutes per shower, 3 showers a day, kind of an operation. It does minimize the temperature drop in the hot water piping. Insulation will minimize that temperature drop. So it questions the opportunity to maybe dial back your hot water heater a degree or two. Whether that will actually happen, I'm not sure. There's a lot of other reasons we've talked about for maybe not doing that, but there might be some savings there. I think the key savings are during the cool down phase. There's no doubt that insulation can delay that exponential cooling function and can maximize the chances of avoiding cold start. And a cold start is you turn the shower on, you have to wait your 30 to 45 seconds to a minute to get in the shower. All that time, that hot water is going down the drain and is being wasted. Not only are you wasting the water, you're wasting the energy to heat that water up. So let's take a look at that. Insulation does reduce the rate of cooling during the cool down phase. Some of the data says that if your pipe size is 1/2 inch, it can double the cool down phase. Uninsulated would be about 10 minutes, like I drew the graph. The insulated would be about 20 minutes of cool down. 3/4 goes from 15 to 45, and 1-inch pipe quadruples the cool down time from 20 minutes to about an hour and 20 minutes. So there's an opportunity to avoid what I call the cold start. And let's take a look at the economics of a cold start, or the cost of a cold start. So again, let's assume a 1-inch copper line, 25 foot long. There's about 1.07 gallons of water in that line, and you waste about 25% more than that. So you're going to waste about 1.33 gallons down the drain waiting for that temperature to come up to an acceptable value. So the energy penalty for that waste, the energy waste is about 776 BTUs. And again, using 12 cents a kilowatt hour, that equates to about 2.7 cents per cold start. Now, I'm going to use a cost of water and sewer in Columbus, Ohio, which was my water bill, 1.3 cents a gallon, about $13 per 1,000 gallons. And the cost of wasted water is 1.7 cents. So add those two together, you're going on a nickel per cold start. So you can save about a nickel, 4.4 cents, by avoiding a cold start. And there's ways to do that. You can get up in the morning, you can take your shower, you can get your wife to take her shower, you can get your kids to take their shower. If they all take them back to back, then you'll avoid that cold start. But trust me, that's going to be hard to do. That's going to be hard to get your family to take showers when you want them to take showers. So insulation is an opportunity to stretch out that window, the window of opportunity for avoiding cold starts. So let's say you can avoid 2 cold starts per day, 365 days a year. That equates to about $19.71 in energy costs and about $12.41 in water costs. So now if you take the energy cost savings during usage, the 15 cents a foot times 25 feet is $3.75. The energy cost of avoiding the cold starts, $20. The water cost of avoiding cold starts is about $12.41. So the total cost savings over a year, avoiding 2 cold starts a day, is approximately $35 a year. Same $6.12 to insulate the 1-inch tube or pipe, $153 a year. So the simple payback period is now 4.3 years, and the return's about 23%. So now we're back in the ballpark of what is justified from an economic point of view. Again, what if you didn't avoid 2 cold starts a day, maybe you only avoided 1 cold start a day, depending on the usage patterns? Well, you're still talking about probably an 8-year payback. And it's still going to be economic feasible, considering that that building may sit there 50 years, it may sit there 80 years, it may sit there 100 years with insulated piping in it. So, we're thinking about insulation differently. We're thinking about insulation not only saving energy, but also saving water. And for domestic hot water recirculating loops, insulation is a no-brainer. For branch lines, insulation may be justified depending on the frequency, duration, and pattern of use, and the cost of energy and the cost of water. And considering the anticipated escalation of the cost of energy and the relatively minor incremental cost of insulation and the long service life of domestic hot water piping systems, we feel that Energy Code should require insulation on all domestic hot water piping, like the IATMO code currently does. So thank you for your attention. I'd be happy to take a few questions if anyone has any.
Thank you, Chris.
Thanks. Rich Prospel from ASSE. The figures you're using were all for 1-inch fiberglass insulation. How would that relate to the closed cell or armor flex type insulation? Would the numbers be similar, better, or worse?
Those insulations are typically more expensive than fiberglass in that pipe size. As you go smaller in pipe size, there may be some benefit there, and larger in pipe size, it will kind of go the other way. So 1 inch is kind of in the middle on that.
I've heard, and I could be wrong, that there's hot water heaters that heat up instantaneously and don't just fill a tank. I'm trying to find out, in general, do they exist, and why aren't they in general use?
Well,
if they do exist.
I believe they are in general use in a lot of installations, and they do minimize the standby losses. You don't have to keep that tank hot all the time. But as far as the distribution system, the piping from that, it's really the same story. That's the heat source, and you've got to either fire a circulation loop to minimize the time, the waiting time, or use some other technique of minimizing that time, whether you're talking instantaneous heaters or whether you're talking central tanks. Of course, the advantage is you can get that instantaneous, you may be able to get that instantaneous heater closer to the usage, and that's going to minimize the wait time too.
To expand on that, there's about 7 million water heaters sold in the United States every year. And there's about a 50-50 split between gas and electric. And by comparison, there's probably about 300,000 tankless water heaters sold. And it's probably, it's a matter of cost for both the unit and for the installation. Do we have any other questions?
Yeah, Bill Erickson. Is there any innovations or new technologies coming out for insulation material that might be smaller, as we all fight for space in ceilings and walls in buildings? You know, I'm wondering if that's a possibility.
Yeah, there is some new technology. Some of the nano-based technology is becoming available. Traditionally, we've always thought that you know, the conductivity of still air is about as good as you can get. About 0.2 is about as good as you can get on an insulation. But some of these flexible aerogel insulations are down below that, down maybe 75% or lower than that. So there's opportunity there. Has more expensive typically, and so it hasn't caught on yet, but that is new on the horizon.
We have another question over here.
It's Ivan Steele from IPEX. I'm just wondering if any of the codes, including the IATMO one, take into account the R value of the pipe in the requirement of insulation thickness.
I believe they do in determining the requirements. The R value of the pipe is required, but there's no, I take that back, the ASHRAE 90.1 does have an allowance or a capability of looking at other base materials than metallic materials. So,
like the IATMO one would be a certain thickness regardless of pipe?
Yes, that's correct. The ones basically the same thickness required no matter what, whether it's copper or plastic.
Thank you.
Do we have any more questions? Hey, we have one more in the back.
Yeah, basically the same idea. How much better would, say, PVC pipe be compared to a copper pipe in terms of heat loss rate and cost?
As it's bare pipe, there would be some advantage, but after it's insulated, the base material doesn't make a whole lot of difference once you put a 1/2 inch insulation on it. PVC plastics have a K of about 1. Insulations have a K of about 0.25, so it's about a 4 to 1 ratio. So the difference in heat loss between an insulated copper pipe and an insulated plastic pipe is probably not real great.
Craig Solover.
Yeah, he's right. If they're insulated, there's little difference. One thing, though, that Carl Hiller's research showed on PEX pipe is it has a lower heat transfer value in terms of conductivity than copper. But it loses heat more rapidly than copper because at that point, once you get the external surface to the temperature of the inside, as radiant heat, it radiates the heat much quicker than the copper does. So, which seems counterintuitive, but that was the basic science behind it. So once you insulate them both, it starts to become a lot more equal.
And I might add, there is a tool that I actually use to make these calculations called the 3E Plus program, and it's available free of charge on a website called pipeinsulation.org. And you can download that program and play with different emittance surfaces, which is exactly what you're talking about, and see what the impact copper versus plastic versus steel is.
Thank you, Chris.
Thank you.